All right, today we're looking at polar areas. Now this is a little bit different than just area under a curve because we have to deal with the area of a sector. Polar areas comes down to the area of a sector and taking infinitely small sector areas and summing them up. Similar to how when we first did integrals, we did infinitely small rectangles and summed up those areas. So area of a sector, if you remember from geometry, find what I'm looking for, there we go. If you remember from the geometry, area of a sector is r squared over 2 times theta. So that is the area of a sector. So we're going to be turning that into a integral and using this formula for area of a polar equation. Integral from a to b, 1/2 r squared d theta. Now, most of these are going to be set up but do not solve problems. Well, you will have some that are actually solving the equation. So let's start with this first one. This is a cardioid. And if we were to graph the cardioid, we'd get something like, oops, not that. Something like this. All right, so there's our cardioid. And we want to think about the area of that whole cardioid. So the big question for a lot of these is going to be what's going to be our bounds. We know the formula. R squared, so 2 plus 2 sine theta squared d theta. What are our bounds of this though? Well, the bounds of a cardioid are going to be the same for almost any cardioid, but the bounds of a polar equation in general are going to vary based on what area we're looking for. In this case, looking for area of a cardioid. So if we were to go through our values, we plug in 0 here, we get 2. So that's this first one. We plug in pi over 2, we get 4. So that's the second one. So this covers this part of the graph. We plug in pi, we get down here. So now we've covered this part of the graph. We plug in 3 pi over 2, we're at 0. So that's going to cover this part of the graph. And then we plug in 2 pi, we get back to 2, which is this part of the graph. So in this case, we're going to go all the way from 0 to 2 pi. But that's not the only way we can do it. This graph is symmetric. It's symmetric along that y-axis. So if we could find bounds that represent the start and end of that y-axis. So for example, if we could find a bound that represents this right here, or a bound that represents the other way, then we could feasibly use that to solve for the area as well. It's just if we were to only do half of it, we'd take the formula and double it. Now this is where the AP exam will really kind of focus when it comes to problems like these, is can you match the answer choice with the correct bounds? Because they may not have this answer choice on there. They may instead have said, okay, let's do pi over 2 to 3 pi over 2, which is half of it. And instead, double that. And there's an infinite number of bounds you could use. You could use 2 pi to 4 pi. That would be another path around this cardioid, but that one wouldn't need to be doubled because it'd be the whole cardioid. Or you can use 3 pi over 2 to 5 pi over 2. That would be from here around to this part. And that would still be half of the cardioid. So it's all about understanding those bounds. Let's look at another example. This one, we have a rose curve, 3 cosine 3 theta. So that's this curve right here. Okay, and so this is our rose curve. It wants the area of one petal. So we have our area formula. And the rose curves are the ones where they really do this a lot because understanding how they graph is super important. In a rose curve, if it's odd or even, it determines the number of petals. We've seen that before. But it also determines the number of times you go around the graph. Odd ends, while it has the same number of petals, it actually goes from 0 to 2 pi, it goes around the graph twice. Oops. If it was an even number of petals, for even, from 0 to 2 pi, it would go around once. So it's a lot to remember about how many times does it go around and things like that. Instead, what would probably be easier is just remembering how to find one petal. Well, every single petal, if we look, every single petal starts and ends at the origin. So if we can find two consecutive zeros, then we can find the start and stop of one petal. So let's find those. 3 cosine 3 theta equals 0. Cosine 3 theta equals 0. 3 theta is equal to pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, and 11 pi over 2. Divide them all by 3, and we get all these right here. Pi over 6, pi over 2, 5 pi over 6, 7 pi over 6, 3 pi over 2, 11 pi over 6. So these are all the times where it touches 0. All right, so that's a lot of times where we touch the origin. But it seems like a lot. The fact of the matter is, any two consecutive zeros creates a petal. So here's the first 0. The next 0 is going to be the end of the petal. Here's the first 0. The next 0 is going to create the end of the petal. Here's the first 0. The next 0 is going to create the end of the petal. So two consecutive zeros will create the end of the petal. So we can make any of our bounds be zeros as long as they're consecutive zeros. All right, so we could do pi over 6 to pi over 2, or pi over 2 to 5 pi over 6, so on and so forth. We could even get more specific. We could say, okay, I'm smarter than this problem. This is half of a petal. We know where this starts at. This starts at 0. And then half of the petal would end at this first 0, the very first 0 we find, which is pi over 6. So we would say 1/2 integral from 0 to pi over 6, 3 cosine 3 theta. And since that's half the petal, we could just double it. So once again, an infinite number of ways we can write these integrals, but you have to be able to understand what are the bounds that will give me what I want. What are the bounds that will give me what I want, and how do I need to alter the function to fit those bounds? All right. Similar thing that happens here. Find the area inside the inner loop. So we have our inner loop graph. Oops, there. That's too much. I don't know what I'm doing now. There we go, much better. All right, so looking at this one, if we want the inner loop, we need bounds that represent the inner loop. We have 1/2 integral, and then our equation, 1 minus 2 sine theta squared d theta. So we need bounds that represent the inner loop. Similar to the rose curve, the inner loop starts and stops at 0. We have 1 coming in from this side, 1 coming out on this side. And that bounds the inner loop there. There's our inner loop. So we need to find the zeros. Okay, easy enough, just like the rose curve. All right, sine is equal to 1/2 at pi over 6 and 5 pi over 6. And you're going to start thinking to yourself, well, I'm really good at this. Let's just add some other zeros and see the other ways we can do it. So we could go around again, 13 pi over 6 and 17 pi over 6. Or go the other way, negative 11, negative 7 pi over 6, negative 11 pi over 6. All right? And you're going to think to yourself, okay, just like the petals, any two consecutive zeros will work. But that's an issue. Because if we look at this inner loop, this pi over 6 is the start, and this 5 pi over 6 is the end. Because if we look, the inner loop starts in quadrant 1 and ends in quadrant 2. If we tried to do any two consecutive zeros, some of them might work, like pi over 6 to 5 pi over 6. But not all of them. If we tried 5 pi over 6 to 13 pi over 6, that would be the end of the loop, which is this part right here, around the whole thing until we get back to the inside of the loop. that would not be just the inner loop. That would be the whole curve. And that wouldn't work for us. So we're not going to be using any two consecutive zeros. For inner loops, you're going to have to be very specific about which zeros you pick, making sure they represent the start and the end of that loop. Okay, let's look at another one. Last one we're going to look at is a lemniscate. Now, here's our lemniscate. We have 4, 4. Now, I'll give you your own time to graph it in the calculator. I'm not going to worry about graphing it because I know what it looks like and how it does it. Similar to how we graph parametrics, change your calculator mode to polar and try graphing this and just see some of the things that happen. What you'll notice is from 0 to 2 pi, if you actually graph r squared, which the only way you can do is by using the plus r and minus r, so one function for that's positive, one that's negative, you'll see that it actually graphs twice on that bound. That doesn't work for us. So we need a good set of bounds. A lot of people will change, okay, let's do 0 to pi over 2. But that becomes a problem. Because if we look at this right here, this equation that we created for r, if we get a negative there, that's not going to give us anything back. So we need to figure out where this is equal to 0 so we don't end up plugging in a negative. And it's equal to 0 at pi over 4. And so once it hits 0, it crosses into the negatives and you start getting negatives in the square root. And so we want as small as possible. So we're going to go 0, which is here, that's where we start, to pi over 4, which is where it hits 0. Now, if you'll notice, that's only 1/2 of one loop. So if we're going to do that bound, integral from 0 to pi over 4, and it's already giving us r squared, so we're going to say this is 16 cosine 2 theta. Okay? If we're going to use this, then we have to consider what all that covers. Well, this covers 1, 2, 3, 4 parts, so we need to multiply it by 4 to give the whole thing. And so it's 4 times 1/2, which is 2, integral from 0 to pi over 4, 16 cosine 2 theta. And this is one of the ones where they might actually ask you to solve. These can be solved pretty straightforward with just a u sub on 2 theta and solved. I'll let you solve that on your own. All right, that's it for polar area day 1. We'll have another video for day 2 tomorrow. You all have a great day.